Hello students. In this video, I am going to discuss solution of a JEE Advanced 2024 question. See, this question says there are two beads, each with charge Q and mass M, are on a horizontal frictionless and non-conducting circular hoop of radius R. One of the beads is glued to the hoop at some point, while the other one performs a small oscillation about its equilibrium position along the hoop. The square of angular frequency of a small oscillation is given by. So we have to find the angular frequency and we have to basically square it. So question is something like this. See here. So we are going to discuss this question by two methods. Okay, one by force method and the other by potential energy method. Okay. So let's see. There is a charge. Suppose it is fixed here. This one we are assuming is fixed. This one is fixed. Okay, and this one oscillating. This is oscillating like this. Okay, it is oscillating. So it is not vertical. This is horizontal fixed ring. This ring is smooth actually. Okay, so we have to find time period of angular frequency of oscillation here. Okay, see this motion we can prove that will be SHM only for a small oscillation. Okay, for large oscillation it won't be SHM. So if it oscillates, if it undergoes a small oscillation, then value of force on this ring will be almost nearly constant. Okay, it will be nearly constant. Okay, so let us say that value of force is something like this. Okay, force is acting on this one like this. This is the direction of force. And let us call it F. Okay, this angle is theta. So if you calculate this angle and this angle, okay, these two angles will come out to be theta by 2 and theta by 2. Okay, so therefore opposite angle, this will also be theta by 2. So if you resolve force tangentially and normally, okay, so force you resolve in normal direction and tangential direction, it will come out to be F and cos theta by 2, and this side you will get F sine theta by 2. That's what you get, F sine theta by 2. This side force is F sine theta by 2. Okay, now you see, if we calculate torque about center, let us call it O, then this force will not produce any torque. Okay, and this force, there will be a force in this direction which will be normal reaction because of the ring. This force is also passing through center, so this force will not also produce any torque about center. Only this force is going to produce a torque. Okay, so let us write here equation of motion for rotational motion. Torque equal to I alpha, where I is moment of inertia of the bead. So this bead is oscillating, its mass is, let's say, M. Okay, so torque, if we calculate the torque, this will be force and its perpendicular distance from center will be R. So it is F sine theta by 2. Okay, and perpendicular distance R. This torque is a restoring torque. See, we have displaced it anti-clockwise, and it is trying to bring it bring it back to its initial position, okay, or equilibrium position. So therefore this torque is a restoring torque. We are putting a negative sign here, okay. Or if you use direction of torque and direction of angular displacement, you will find that the two directions are opposite. So that's why here we are putting negative sign, okay. So moment of inertia will be mass into distance square and alpha. So alpha we can write, alpha is basically angular acceleration. So that we can write as theta double dot. Okay, or you can just write alpha, okay, if you want. So here you see 1 R will cancel out. See, this angular displacement is a small. Okay, so in place of sine theta, we'll write theta. Sine theta by 2 will write theta by 2. So this is minus F theta by 2, and R is equal to M R square and theta double dot. So we are getting here theta double dot is equal to, you see here, we are getting theta double dot is equal to minus F divided by M, and 1 R will cancel out. So 2 MR and theta. You can see theta double dot angular acceleration is proportional to negative of angular displacement. So therefore this is simple harmonic motion. as I said, when this particle is oscillating, force on this particle will almost remain constant. So this force is just like a constant. Okay. So therefore, this term will be angular frequency square. So we can write omega square will be equal to F divided by 2mr. Now let's put the value of force. See, there is a charge Q and there is charge Q. Separation between these two charges is almost equal to 2r. Okay. So this will be force according to Coulomb's formula, Q square upon 4 pi epsilon naught, and distance will be 2r whole square. This is a force, and we already have here 2m and r. So therefore we have here Q square upon, ठीक है, यहाँ से 4 आ जाएगा और ये 2, ठीक है. So 16 and 2 32 हो जाएगा, 32, ठीक है, pi epsilon naught, and we get here m and multiplied by r cube. So that's the answer. Okay. So this is angular frequency square. So if you assume that force almost remains constant, then you can very easily answer this question. Okay. So this is method 1. Okay. So therefore you can see here this option, this is given in option B. Okay. So this option B is correct. Okay. Now you see, let us do it by another method. Okay. So method 2. So what I'll do, I'll see here I have used force and torque, etc. Here in method 2, I'm going to use potential energy. Okay, so you see this is radius and this is also radius. Okay. So if you calculate this side, see, if you calculate this side, okay, this is radius and this side is also radius. Okay, radius. So by using cosine formula, you can calculate this side. Okay, this angle is theta, so this angle will be pi minus theta. Okay, so we have this kind of situation here. You see, something like this, and it is something like this. Here there is a charge and here there is a charge. Okay, this angle is pi minus theta. Okay, this is radius and this is also radius. So you can calculate this side using cosine formula. Okay, or you can calculate this using sine formula also. Okay, so this angle is theta by 2. Okay, this angle is also theta by 2. So using sine or cosine formula, whatever you calculate this side. Okay, so let us call this side as D. So we will write sine formula D divided by sine, and here pi minus theta. This will be equal to, if I'm using this side, then opposite this angle, then opposite side is R. So this is R upon sine theta by 2. Okay, so from here you will get D is equal to 2R and cos theta by 2. This we get. Okay, so D is this. So now let us write potential energy. Interaction potential energy of these two charges. There is charge Q here and there is charge Q here. So this will be equal to Q square upon 4 pi epsilon naught and D. Now let's put the value of D here, this separation. Okay, so this is Q square upon 4. This becomes, when you put the value of D, there is a factor of 2 here. So 8 pi epsilon naught and R, and here there will be cos theta by 2. So that I'm taking to numerator. So you will get sec theta by 2. That is the interaction potential energy of these two charges. All right. Now, see, we have gotten the interaction potential energy. Now, angular frequency, if you know the interaction potential energy, then angular frequency is written like this: K theta, okay, and divided by moment of inertia. Where K theta is written like this, K theta is second derivative of potential energy, okay, at equilibrium position. So which is theta equal to 0 here. Theta equal to 0 is the equilibrium position. You can see here. See, this at this position, this charge can stay at rest permanently. Okay, so this is the equilibrium position. Okay, so at this position, theta is 0 actually. Okay, so you can see. So if we calculate K theta, okay, by differentiating potential energy, and we put the value of K theta here, we'll get angular frequency. Okay, so let us do this. Okay, you see here, we have U equal to this much. So if you calculate du by d theta, okay, you will get here a factor of 1 by 2 will come here. So you will get Q square upon 16 pi epsilon naught and R, and here you will get sec theta by 2 and tan theta by 2. Okay, now again differentiate it, d2u by d theta square. Okay, you will get here Q square upon, again when you differentiate, you will get a factor of 1 by 2 outside. Okay, so you will get 32 pi epsilon naught and R here. Okay, that's what we get. And now let's differentiate sec theta first. So it will give you sec theta by 2 and tan theta by 2, and already we have tan theta by 2. So you will get here tan square and theta by 2. Plus when you differentiate this tan theta by 2, you get sec square and this sec. So this becomes sec cube theta by 2. Okay. That's what we have. And we are evaluating this at theta equal to 0. So at theta equal to 0, this term becomes 0, this term becomes 1. Okay. So we are getting this is equal to q square upon 32 pi epsilon naught and r. That is du by d2u by d theta square evaluated at theta equal to 0. Okay. So this we call k theta. You can call it angular force constant, okay, or torque constant you can say. जैसे force constant होता है ना kx, k लिखते हैं हम लोग spring constant के साथ k, so that is force constant. You can call it torque constant. Okay. All right. So now omega is equal to root under, as I said, k theta divided by moment of inertia. So k theta is this moment of inertia here. Okay. See the bead in this figure. You see this is the bead. It is oscillating like this. So we can say that it is rotating about an axis passing through center here. Okay. So its moment of inertia about this axis will be equal to mass into distance square. Okay. So we can write here this moment of inertia will be just equal to mass into distance square. Okay. So let us put this here. So this is q square upon 32 pi epsilon naught and here r. And when you put moment of inertia, see moment of inertia mr square, you will get another r square here. So this will become r cube and m. Okay. So therefore, omega square will be equal to q square upon 32 pi epsilon naught m and r cube. So again, this answer is same as the previous one. Okay. So this option B is correct here. Okay. Yeah. This option B.